Hello friends, good morning. As a part of thermodynamics, in this video I am going to present further aspects of thermodynamics. In the first video, I had mentioned few basic properties. Now we proceed ahead. Be sure this video will be very interesting and very useful as well. Thermodynamic process. Nature of work and heat H. The relationship between these two is W over H equal to J, called Joule, mechanical equivalent of work, and the Holder unit calorie is related to joule as 4.184 joule is equal to 1 calorie. Thermodynamic equilibria. Thermodynamic equilibria may be mechanical, thermal, or chemical. Components of energy or work. Energy is equivalent to work as both are measured in joule unit. Work comprises two factors, intensity factor and capacity factor. For example, with certain mass m is to be lifted against gravity g, a height h, then mass into g constitutes intensity factor and height h implies the capacity factor. Total work done becomes equal to the product of these two factors, that is mgh. Likewise, if certain amount of water is heated by supplying heat q, temperature is the intensity factor and its heat capacity is the capacity factor. The first law of thermodynamics. This law can be proved with reference to the figure shown. It emerged from long experience that a perpetual motion machine can never be a reality. Obviously, if the internal energy change accompanying the change from state A to state B, that is path 1 shown in the figure, is EB minus EA equal to delta E, that for the reverse path, that is path number 2, second path, that is from state B to state A, must be equal with opposite sign, that is EA minus EB, EB, EA minus EB equal to delta E prime must be equal to delta E. Obviously, the internal energy change accompanying the process would not depend on the path. Instead, it depends on the state of the system. That is, the internal energy change accompanying the process would not depend on the path. It is state variable. Accordingly, cyclic integral of dE will be 0. The first law can be proved with reference to the figure shown here. Now let us assume that following path first, the system absorbs heat Q and performs work equal to W on the surroundings. Evidently, delta E equal to EB minus EA equal to Q minus W. On the path second, delta E prime equal to EA minus EB equal to Q minus W. In general, the first law of thermodynamics is written as delta E equal to Q plus W, where the heat Q and work W are given positive or negative sign as per the convention. Work done by the system on the surroundings is given negative sign, negative W. Work done on the system by the surroundings is given plus sign, positive W. Heat added to the system plus Q, heat given out from the system minus Q. Now let us assume that following path 1, the system absorbs heat Q and performs work equal to W on the surroundings. Evidently, delta E equal to EB minus EA equal to Q minus W. For the path second, delta E prime equal to EA minus EB equal to Q minus W. In general, the first law of thermodynamics is written as delta E equal to Q plus W. The heat Q and work W are given opposite positive or negative sign as per the convention mentioned earlier. PVT work. Let us think of a thermodynamic system consisting of n moles of an ideal gas in the state designated to. It means that its state variables are well defined. That is, internal energy EA, enthalpy HA, entropy SA, temperature T1 or T, pressure P1 or P, and so on, so forth. Now, some operation like heating or cooling or any other is performed on the system so that it changes its state from A to B. As a result of this operation or process, some or all its thermodynamic variables get changed to reach new values, e.g. EB, HB, SB, T2, P2, etc. The path from state A leading to state B may be reversible or irreversible. In addition, it may be a constant temperature process, that is isothermal process, T1 equal to T2, delta T equal to 0, or adiabatic, that is Q equal to 0, or isobaric, that is P1 equal to P2, or constant volume process, that is dV equal to 0, or isoenthalpy process, dH equal to 0. For an isothermal process, internal energy E, which is due to various quantized energies of atoms and molecules, rotational, vibrational, electronic, etc., plus translational energy, remains unchanged because for ideal gases, E depends on T only. For real gases, E is a function of T and V, or E is a function of T and P. For a constant enthalpy process, dH equal to 0, it is called as isoenthalpic process, for example, the Joule-Thomson process. For a constant volume process, dV equal to 0, the PV work is 0. Expansion against zero pressure is called free expansion. No work is done. Reversible and irreversible processes. A process is said to be reversible if it is being carried out in finite assembly slowly so that it continuously remains in mechanical equilibrium with the surroundings. Although this concept of reversibility is very useful in deriving various thermodynamic equations, it continues to be imaginary and theoretical, not practical one, because such a process would require infinite steps and infinite time for its completion. In fact, all natural and laboratory processes are irreversible in nature. That is to say, they occur at some definite and measurable rate. An example of reversible and irreversible process is given here for clarity. Let us begin with the process. A non-insulated cylinder of volume V contains n moles of an ideal gas. An adjustable piston of area A, which is insulated, weightless, and frictionless, is fitted and held in position using microfractional weights. Initially, the inside pressure of gas is P, which is balanced by the external pressure P external. When the external pressure is infinitesimally brought down, P external minus dP, the piston moves outward by an infinitesimal distance, that is from initial height L to L plus dL. Obviously, this process is accompanied by infinitesimal increase in volume from initial volume V plus dV. where dV equal to A into a dl. And then infinitesimal decrease in pressure, it is from P to P minus dP. It is in equilibrium with P external minus dP. The temperature T is kept constant throughout the process, and it is called an isothermal process of gas expansion. This is possible when infinitesimal amount of heat dQ is being absorbed from the surrounding is not zero, positive in state. And as a consequence of this, the system is maintained in thermal equilibrium with the surroundings. Process is repeated excessively large number of times, and it is done in a continuous manner. Therefore, the total work done by the system on the surroundings can be calculated by taking the sum of these infinitesimal steps, that is using calculus. These two figures show very clearly this. The first figure shows reversible volume expansion of an ideal gas from P1 V1 T2 P2 V2 T constant. The second figure shows reversible volume compression P1 V1 T2 P2 V2 T, again at T constant. Their limits are V1 to V2, pressure P1 to P2, and dW equal to minus P external into dP minus dP into dV. Ignoring the infinitesimally small term dP dV and replacing P external by the equivalent internal pressure P, both being in equilibrium, we have dW equal to minus P dV, which can be written as minus nRT dV over V using the ideal gas equation. Integration of the inexact differential dW yields W, whereas integration of nRT dV over V using lower limit V1 and upper limit V2 yields nRT ln V2 over V1 or minus nRT into ln P1 over P2. Replacing the minus sign, it becomes nRT ln P2 over P1. Formula for integration has been suggested here. Integration of 1x gives log x plus constant of integration I. Therefore, work done by the system on the surrounding is equal to minus nRT ln V2 over V1 minus 2.303 nRT log V2 over V1. Note that whereas V2 is greater than V1, initial pressure P1 is more than final pressure. Therefore, the work done in volume expansion has negative sign, positive sign for compression. By exactly the same logic, we can show that the reversible isothermal compression of an ideal gas from initial volume V1 of pressure P1 to the final volume V2 of pressure P2 to infinitesimally small steps dW equal to minus P dV leads to positive work given by the equation W equal to minus 2.303 nRT log P1 upon P2, where initial volume V1 is greater than V2, initial pressure P1 is less than P2, hence W is positive. Thus, in magnitude, expansion work is same, equal to compression work or the reversible process, both having opposite sign. In the process of expansion of the ideal gas from initial volume V1 of pressure P1 to final volume V2 of pressure P2 is less than P1, is carried out rapidly and irreversibly against constant external pressure. The work is calculated using formula minus P external into V2 minus V1. Note that the magnitude of irreversible work is less than reversible work because in the former case P external is almost equal to the internal pressure, P1. In the case of irreversible expansion, P external is the atmospheric pressure, which is much less than the internal pressure. Adiabatic process means Q equal to 0. Applying the equation delta E equal to Q plus W, we conclude that delta E equal to W. Both sides are negative. It means that the heat absorbed from the surroundings being 0, expansion work is done at the expense of internal energy, which decreases. Therefore, temperature also falls. Cooling effect. Comparison of isothermal expansion and adiabatic expansion. In adiabatic expansion, Q equal to 0, T falls. In isothermal, T constant. We will begin by assuming the following values and referring to the figure. Isothermal expansion. Initial value of volume V1, Vi, final Vf. Initial pressure Pi, final pressure P iso. Adiabatic expansion, initial volume Vi, initial pressure Pi, final common volume Vf, and final pressure PADF. Isothermal process. Pi Vi equal to P iso Vf, that is Vf upon Vi equal to Pi upon P iso. Adiabatic process. Pi Vi power gamma equal to P adiabatic Vf power gamma. It means Vf upon Vi whole power gamma equal to Pi upon P adf. Since expansion means V final greater than V1 or V initial, and therefore V final power gamma greater than V initial. It implies V final upon V initial power gamma greater than V final upon V initial, because gamma is more than 1 and gamma is the ratio Cp upon Cv. Accordingly, P initial or P area greater than P initial or P iso implies that P iso is more than P area. Comparison of isothermal T constant expansion and adiabatic expansion. The above relationship can also be proved by assuming common final pressures. The similar conclusions emerge. Also, Charles' law is in consonance with these conclusions. These things can be shown here by the diagram. Are the two processes, isothermal and adiabatic. The area of work has been shown. For adiabatic process, the area is less than for isothermal process. Similar conclusions can be drawn in alternative way also. In conclusion, we can say that reversible process gives more output than irreversible process. And work done in isothermal expansion is greater than work done in adiabatic expansion. These are the conclusions. That was the end of the slide. Please like and subscribe to this channel, chemistry_gist. Once again, I must remind you, thermodynamics is very, very important for all branches of chemistry. The subject is so important that it is useful physics, chemistry, biology, economics, sociology, and all other studies, including political science. Therefore, as a chemist, we must understand thermodynamics basic principles thoroughly and clearly. We have finished 2 videos. Many more videos on this topic will be taken up because the topic is very exhaustive, very useful, and not difficult to understand. Little bit of mathematical derivations are involved. Those who are from biology background need not fear it. Little understanding of differentiation and integration will help you. So be sure if you repeat these things a few times, you will follow it properly and adequately. Thank you very much. Thank you.